Meet Tim Rickel. He works for a company called Arc Energy, and they design and manufacture all kinds of vessels and products for the oil and gas industry. Today we're going to be taking a deep dive into one of the popular treatment processes commonly referred to as glycol dehydration. Join Tim, my interns, and myself as we explore this topic in depth. Excuse me, sir, what do you think glycol dehydration is?
Is that like when you drink too much glycol at a party and you get super dehydrated?
No, don't drink glycol. Yeah, that's definitely not what glycol dehydration is.
The whole purpose for your dehydrator is, of course, to take the water vapor out of the natural gas.
Now, the process can seem quite complex, and indeed, even to those in the oil and gas industry, you might not even know much about the process. It seems that most of the need for dehydration of natural gas occurs in the midstream sector, and areas in the upstream sector where the natural gas is compressed or produced at high pressure. Now, the high pressure is an important note. The oil and gas industry, specifically the upstream part of it, has to deal with what Mother Nature gives up from the reservoirs deep below. And a majority of the time, it's going to give us gas that has water naturally entrained in it. So typically, the hotter the gas, the more water you're going to have in it. And the amount of water is actually measured in pounds per million standard cubic feet. The higher the pressure of the gas, the more likely it would be that a hydrate could form, which are basically natural gas ice plugs that can dangerously freeze off entire pipelines.
Okay, so at this point in the video, you guys might be asking, well, why do we need a dehydrated gas to begin with? Well, when water and hydrocarbons are cooled and compressed, it basically precipitates, and that's exactly what hydrates are. These ice crystal formation cause a lot of problems for engineers, such as pipeline corrosion, subplugging, slugging, and poisoning of downstream catalysts. As engineers, we're trying to mitigate as much of these problems as we can.
Now, leaving water entrained in natural gas will also reduce its heating value, which is referred to as BTU or British thermal units. This not only means that the gas is less valuable, but it also means that you would essentially have to burn more natural gas to heat your home if that was handed down to consumers. Excuse me, sir. Do you like it when your natural gas has water in it?
No.
Now, there's so many ways to dehydrate gas, from absorption, adsorption, condensation by refrigeration, calcium chloride, membrane permeation. Now, we're not going to cover all those because that's not what the scope of this video is about. But liquid hydrocarbon dehydration does use some of the technologies that I mentioned prior. Now, TEG, triethylene glycol, is the industry standard for glycol dehydration. And it is for a lot of common reasons. First of all, it's very hygroscopic, meaning it's able to retain a lot of water. Second, it's very stable when it comes to thermal and chemical decomposition. TEG also has a low vapor pressure and is also used for large dew point depressions between 60 to 120 degrees Fahrenheit. And finally, it's available at moderate cost. So our main objective as engineers is to get the gas as dry as we can at the most cost-effective way to do it before the gas gets cryogenically processed and fractionated.
Now that you better understand the background, let's jump into the process of glycol dehydration and the major system components. Let's start by following the gas. Before we dehydrate it, we need to clean it up a bit. This would commonly be done with a filter or coalescer.
Well, we're trying to clean up the gas so that the gas doesn't carry those impurities into the dehydrator. They'll cause the dehydrator to foam and have lots of other issues. The gas comes in here and we'll have condensate and compressor lube oils that need to be removed before we go to the gas dehydrator. This is the coalescer where the gas comes in the back end and it goes through some coalescing elements. The elements are removable and changeable. We have a loop on the first section, and that collects any free liquid that comes into the coalescer. When the gas goes through the elements, and any more liquid that is coalesced will collect in the second loop.
Now, the filters need to be easy to replace, so that's why there's an easy access hatch on the end. Also, there are two pressure gauges, one upstream and one downstream of the filter, so that it's easy to know when they're going to need replaced. Once the gas is cleaned of contaminants, the actual dehydration takes place in what's called the Contactor Tower.
This is the Contactor Tower. In the bottom, there's an inlet scrubber. The gas comes in here at the bottom, and there's an inlet scrubber. So any free liquid will be removed before the gas goes up through the tower. Where the glycol comes in at the top, and the gas is going up from the bottom, and we're making contact and the glycol, triethylene glycol, is picking up the water vapor from the gas as it comes down through the tower. In the very top, there will be a mist extractor removing any glycol mist so you don't lose it down the gas line. The gas then exits the heat exchanger and goes on down the line. Now, to take a little closer look at what's in this tower, this is a bubble cap tower. These are bubble caps, and there's 10 of these trays in this tower. So you have glycol that comes down and it fills up this side, comes over, and then goes down this downcomer. As the gas comes up through the chimney and around and through the slots on these caps. And that's why it's called a bubble cap, because as the gas comes through the slot, it creates bubbles. And that's what makes the contact between the gas and the glycol. So there's 10 of these trays in this tower, and obviously much bigger around and many more caps in this larger tower. So each time it comes down through the downcomer, it turns around, the liquid fills up, and then goes down to the next tray, and back and forth it goes through 10 of these.
Column packing is a second type of contactor tower. Now this sounds exactly what it's like. There's a column filled with a packing material that allows for the components to be in constant contact with one another. Now this packing material allows for a greater interfacial area for vapor-liquid contact. This leads to a greater separation efficiency, and this type of contactor tower handles foaming better than the bubble cap tray tower.
So once the gas has been dehydrated, it's going to typically move on to the sales and measurement point of the facility. Now the triethylene glycol is not cheap, so why not recycle it in the system? In fact, it can usually be used for months at a time. However, we can't just keep recirculating the same glycol that's come out of the bottom of the contact tower straight back into the top, because it's saturated with water. And that's what we call rich glycol, is what comes out the bottom of the tower. So how do you think we get the water vapor out? We heat it up and turn it to steam. To achieve this, we use a piece of equipment commonly referred to as a reboiler or a regeneration unit. But before we take the rich glycol into that, we need to make sure that it doesn't have any entrained gas, condensate, or free water. Thus, some systems run the rich glycol from the contact tower through a flash separator before it takes it to the reboiler.
The purpose of the flash separator is to remove any gas or condensate hydrocarbons that were absorbed by the glycol in the contactor tower. Now the term flashing actually refers to the liquid hydrocarbons immediately transitioning into vapors when they are transitioned from high to low pressure.
And this vessel here in the front is a flash separator where we separate condensate and flash gas from that glycol. The next vessel that's standing up is a charcoal absorber. The purpose for the charcoal is to absorb any hydrocarbons from the glycol that the flash separator didn't get. You want to get your glycol as pure as possible to do the better job picking up water vapor.
Now the reboiler includes a vertical column referred to as the still column, and that's where the rich glycol then enters. The reboiler itself is commonly kept between 350 degrees and 400 degrees, depending on what type of glycol is being used, as well as the operator preferences. If it's too hot or if it's too cold, the system won't work as efficiently, and the glycol can be degraded.
So the major components in this system, of course, are the still column, where the glycol comes in, and then the reboiler, and that's where it's heated up and the water vapor is boiled off.
Now the water vapor from the reboiler then exits the top and enters into what's called a BTEX unit.
Vapors from the still column then enter the BTEX elimination system. BTEX stands for benzene, toluene, ethylbenzene, and xylene. These are captured and recycled because these molecules are considered to be harmful. The contaminated steam is then condensed back into a liquid so that it can be transferred and stored effectively, while any other residual vapors are then burned off.
The vapors coming off of the still column will contain BTEXs, which are carcinogens. And this unit contains a condenser and a separator, which separates off the condensables. The non-condensables then are burned in the combustion.
Meanwhile, the glycol in the reboiler spills into a separate area of the reboiler, in some cases referred to as the surge tank, where it is kept until it gets pressurized and pumped back into the contactor tower. The glycol is now referred to as lean glycol.
After the reboiler, there's a section called a surge tank, and that's where the level will vary because you'll lose a little bit of glycol as you operate, a little bit of weathering. So that's where the pluses and minuses are laid up.
So to what extent do we need to dehydrate the gas? Well, that's where the concept of TEG circulation rate comes into play. Now, circulation rate is dependent on the water vapor content of the gas flow rate, and the gallons of glycol that's required to remove 1 pound of water. Now, if it's too high, you might not have enough heat exchangers in order to properly cool the solution, which leads to glycol losses, foaming, and emissions. And obviously, under-circulating the glycol is going to lead into wet sail gas.
Hopefully you have a better understanding of the process now. However, there's still more. The rest of the complexity of the system comes from engineers being engineers. Yes, we've got to optimize what we can, right? When life gives you a bunch of heat, you throw in a heat exchanger. In fact, you'll find them all over the system. Here's one example.
This particular unit has 4 shell and tube heat exchangers. The purpose for the heat exchangers are to help the efficiency so the reboiler doesn't have to burn as much fuel in the fire tube. The heat exchangers exchange the hot glycol with the colder glycol.
One is also typically placed on the gas outlet of the contactor tower so that the gas can be warmed up by the hot glycol about to enter. This also helps to cool the lean glycol further, which helps absorb the water better once it enters the tower. Now we might as well also capture the gas coming off the flash separator and use that for the burner of the reboiler. So you're also going to have a fuel gas system on the reboiler, which is now self-sustaining. Now, of course, if that was all, that'd be pretty boring. There's also a lot of accessories that enable the system to function and keep it safe. Level controllers, they're all over the place. Temperature and pressure gauges, you gotta know what you're dealing with. Scrubbers and filters, yep, we have those too. They're all over the place. We only went over the major ones. Pressure relief devices, you don't want to overpressure a vessel. Storage tanks, you might want to have some extra glycol on hand. And last but not least, pumps. In fact, you might even have more than one. All right, that's it. Thanks for sticking through this entire video, and we hope it helped you better understand this relatively complex process. A big thanks to our friends at Arc Energy for helping us put this video together. Now, Arc Energy actually supplies high quality equipment to the upstream, midstream, and downstream sectors of our industry, so we can do a lot of videos with them in the future on a variety of topics, and we indeed hope to. But if you as a viewer have any type of recommendations or requests, please drop that in the comments below and we'll take that into consideration as we pick future topics. Thanks again for watching this video. Be sure to like it, share it, and subscribe to our channel. Thanks.